Hello, I'm Dongyu Lee, who is taking Statistical Learning Theory. Let's start analyzing the final project. The papers I have chosen are causal discovery with reinforcement learning on the causality topic and sample selection for fair and robust training on the fairness topic. In each paper, introduction is first explained, and after defining the problem and task, I will analyze the algorithm. Then I will show the experiment results. Understanding causal mechanisms is important in many empirical sciences. In a directed acyclic graph DAG, a node represents each component and an arrow between nodes represents a link indicating a direct causal relationship. A major class of such causal discovery methods are score-based, which assign a score, typically computed with the observed data. Recently, below problems was formulated as a continuous optimization problem by choosing a proper loss function such as log likelihood, and causality was modeled using neural network. The score-based, traditionally used in the process of finding the DAG, uses a local heuristic and a predefined score function. Although these methods for a DAG may have attractive results with infinite samples and certain model assumptions, they are less satisfactory in practice due to finite data and possible violation of assumptions. For these reasons, this paper proposes to use the other method to search for the DAG with the best score according to a predefined score function. Another agent with stochastic policy can determine automatically where to search given the uncertainty information of the learned policy. This is overall RL architecture. Observed data as input and creates a graph through encoder-decoder model. Whether the generated graph is appropriate is determined through the reward function, which will be explained later. And the optimal graph is found by repeating this process. This structure was applied to various data sets and its feasibility was verified. Each variable xi is associated with a node I in a d-node DAG G, and the observed value of xi is obtained as a function of its variance in the graph, plus an independent additive noise ni according to formula. The observed data x, consisting of a number of vector x, are sampled according to the above formula from an unknown DAG. The objective of causal discovery is to infer the causal DAG G using X. Encoder and decoder neural network model is considered for graph generation. The input of this model is the observed data and the output is a graph adjacency matrix. The self-attention-based encoder is used because of its ability to find causal relationships between variables by providing sufficient interaction. The single-layer decoder is to generate the graph adjacency matrix by building relationships between two encoder outputs, ENCI and ENCJ. To generate output, it is sampled according to a Bernoulli distribution with logistic sigmoid function that indicates the probability of existing on edge from Xi to Xj. This paper uses RL as such strategy to find the DAG with the best score. As previously explained, encoder and decoder neural network takes the observed data as input and generates a graph adjacency matrix. Whether the generated graph adequately represents the causal relationship is determined through the reward that consists of the predefined score function and two penalty terms to enforce acyclicity. The paper focuses on the big score, locally consistent for its decomposability. Let x at ki be the corresponding estimate for xki, the ith entry of d components in the case of m observed samples. The first term is the log likelihood objective, and the second term as penalty on the number of edges in the graph G. The paper takes into account acyclicity by way of adding penalty terms to the score function. Although a directed graph G with binary adjacency matrix A is acyclic IFFHA, the minimum over all non-DEX is not easy to find. The indicator function I is used in second penalty terms to induce exact DEX. The reward incorporates both the score function and the acyclicity constraint. Lambda 1, lambda 2 are two penalty parameters. A generated graph with a high reward will be acyclic. Then, the other agent aims to maximize the reward over all possible directed graphs. It is an algorithm for causal discovery. I use the expectation of reward as the learning objective function using the actor-critic algorithm. Pi and psi obtained as a result of training is a parameter of the neural net used for graph generation. Through several iterations, each parameter can be tuned for specific applications, and the inferred causal graph would be the one that is acyclic and achieves the best score. 3 semantic and 1 real datasets are used to compare their approaches to various approaches. LinGAM with both Gaussian and non-Gaussian noise models, nonlinear models with quadratic functions, nonlinear model with Gaussian processes, and SATs are used as datasets respectively. The paper's approach is combined with the big scores under IID Gaussian additive noise, equal noise variance, denoted as RLBIC and RLBIC2 respectively. There are 3 evaluation metrics. First, discovery rate, true positive rate, and structure Hamming distance. That means the cost to get through DAG. This is quantitative result. It shows the learning process of the proposed method RLBIC2 on a linear Gaussian dataset. In this example, RLBIC2 generates several different graphs during training, much lower than the total number of DAGs. The front DAG turns out to be the same as the underlying causal graph. In both linear and nonlinear models, the proposed model outperforms the rest of the existing models. In linear models, RLBIC2 prevailed over RLBIC, and in nonlinear model, vice versa. Next is the fairness paper. I will present in the same order as the previous presentations. While a traditional focus on machine learning is to train the most accurate model possible, trustworthy AI is becoming essential for modern machine learning. Among the key objectives, the paper focuses on fairness and robustness. Fairness is about learning an unbiased model. The main purpose of fairness is to remove bias in the data. The term sensitive attribute is related to fairness because it can lead to discrimination so that model can be biased. Robustness is about learning a model from corrupted data. The purpose of robustness is to compensate for noise in the data. Both of fairness and robustness are closely related to each other because addressing only one of them may have an adverse effect on the other. As mentioned, improving fairness while ignoring robustness may lead to worse accuracy. Likewise, focusing on robustness only may have an adverse effect on fairness. There are several approaches for supporting fairness and robustness together. However, most require a specific model architecture or modify the data itself, but it is difficult to know how. This paper proposes an adaptive sample selection approach for the purpose of improving fairness and robustness. This approach can be used by only modifying the sample step in batch selection, which does not require modifying the model or data. It is based on top of 2 recent research, clean selection for robust training and batch selection for fairness. The proposed method formulates a combinational optimization problem for fair and robust. Sample selection can achieve unbiased sampling in the presence of data corruption. Before an optimization framework is explained, let me introduce ITLM, that is, a robust training method that cleans samples based on their loss functions. ITLM shows accuracy for large noise rates, but unfairness. The unfairness constraints have upper bounds that selected sample of certain set cannot exceed a portion lambda of the selected samples of the class Sy, where phi is whether the data sample di is selected or not, and I is an index set of yz class. Sy is the selected samples for y class. According to ITLM and these assumptions, new loss is derived. Sampling ratio of sensitive groups are adjusted to determine the lambda values. For each batch selection, which sensitive groups should be sampled more or less in the next batch is decided by the fairness of the intermediate model. Then the sampling rates become lambda values used in the fairness constraints. Minimizing the sum of L zeta is equal to first equation, where D is the set of Di. Second and third equation is satisfied where dyz is the subset for the yz class, and one function is an indicator function with new weights wi equal vi plus 1, always positive. Greedy approach is used by sorting all the samples in descending order according to the first equation and selecting the samples as that do not violate any of the constraints third equation. The entire model training process uses weighted ERM. Input consists of trained data, clean ratio tau, and loss function L zeta. Output is the updated model parameter zeta, and for each approach, a clean and fair sample set S is selected using greedy-based method. Then drawn mini batches from S update the model parameter zeta via stochastic gradient descent. Finally, at the end of the effort, lambda values that used in the fairness constraints are updated. The paper uses one semantic data and two real benchmark datasets. The synthetic dataset has many samples and consists of two non-sensitive features, one sensitive feature, and one label class. Each sample is drawn from the predefined Gaussian distributions. Two real data, COMPASS 3 and other sensors 4, used respectively. The former label indicates recidivism, and the latter label indicates each customer's annual income level. For both datasets, gender is used as a sensitive attribute. Two representative group fairness measures are mainly used as an evaluation matrix. First, equalized odds, EO, whose goal is to obtain the same accuracy between sensitive groups conditioned on the true labels. Second, demographic fairity, which is satisfied when the sensitive groups have the same positive prediction ratio. The classifier is perfectly fair when the fairness disparity is 0. Then proposed algorithm is compared with 4 types of baselines: vanilla training, robust training, fair training, and fair and robust training. 10% of labels or targeted labels are either flipped in the training data, and each experiments are repeated 5 times. And the figure is qualitative results. It is performance of LR, ITLM, FR-train, and our algorithm on the synthetic data while varying the noise rate using label flips. As you can see, proposed method achieves the highest accuracy and fairness results compared to the baselines, even the fair and robust training method. It means that noise and bias cannot easily be mitigated in separate steps. Like the synthetic dataset, in the real dataset, proposed method usually has the best or second best accuracy and fairness values. However, FR-train, fair and robust training, also obtains very high accuracy values with competitive fairness. It is assumed that FR-train method takes advantage of its clean validation set to obtain very high accuracy values. To make sure, this paper conducted additional experiments that use validation sets that are less clean. In below table, they checked whether the FR-train shows good performance on all data or if it shows good performance only when the data is cleaned externally. As a result, the proposed method is comparable to FR-train on random data. In addition, this paper conducts an ablation study to investigate the effect of each component in algorithm. As a result, as you can see, each ablation test leads to either worse accuracy and fairness in below table. Therefore, this algorithm is a successful proposal. This is the end of my presentation. Thank you for listening.